There is a growing need for small, high-speed unmanned aircraft system solutions for various military, civil, and commercial applications, including time-critical surveillance with minimal portable operational footprint. Our design, the turbine engine and rocket-assisted drone aerial reconnaissance target, PADAR, focuses on the implementation of a radar system to reduce operational footprint and decrease critical response times. The PADAR launches with the assistance of dual rocket system that it propels to cruise. It is designed for mission legs consisting of radar launch and climb, initial cruise, 2 sets of a loiter followed by a dash phase, return cruise, and descent. The critical mission leg with the high design requirements is during and around the dash stages. The PADAR dash phase is a 2-minute Mach 1.2 dash followed by a 3G turn at Mach 0.9 at altitudes of 15 and 30,000 feet. The design cruise conditions are at Mach 0.65 and 30,000 feet. One of the most critical decisions at the start of an engine design process is estimating the level of technology to be used. The PADAR uses level of technology 4, representing the usage of modern technologies and materials, but not speculating on expensive or uncertain future technologies. The aircraft's weight varies throughout the mission profile due to the detachment of the radar system and fuel consumption. TSFC at critical fuel consumption legs is used to determine the engine design needed to meet all mission requirements. The aircraft is assumed to have a similar drag profile to the F-35. Therefore, initial calculations were done using its drag polar to determine aerodynamic performance numbers. Conducting a parametric cycle analysis yielded an engine model with a pi-c of 21 and TT4 of 3,000 degrees Rankine. This engine, known internally as the Sigma model, was chosen for its balance of good fuel economy and specific thrust, while remaining well within the bounds of technology limits, allowing for safe and reliable operation. The engine is sized through AIDSYS software off-design analysis by considering the model's pi-c, TT4, and other results from the PCA. Additionally, flight conditions such as altitude and Mach number need to be accounted for to find the corrected parameters at the common datum. The max corrected mass flow rate was calculated to be 113.8 pounds per second. This value was then used to find an engine diameter of 1.744 feet. The sized engine was further analyzed to designate throttle operating points and determine additive drag.
Aircraft integration is one of the most difficult and often overlooked aspects of aircraft design. Some of the challenges navigated in this project included structural loading on the wing due to rocket-assisted takeoff, integrating the rocket-assisted takeoff bracket to each side of the wing, interfacing the rockets with the launch rail, as well as propulsion and airframe integration. Constructing the launch rail required a resistance to force in the opposing direction of the rocket thrust, while allowing freedom to move in the direction of the thrust vector. The rocket-assisted takeoff bracket is designed to resist maximum thrust experienced during takeoff and fully release from the aircraft upon rocket motor burnout. The rocket motor is equipped with a nose cone that contains avionics and hardware for autonomous recovery that allows this rocket-assisted takeoff system to be more cost-effective and fully reusable. Finite element analysis was performed on the 2024 T4 aluminum bracket, and it was determined that the system is structurally sound. To accelerate to cruise speed from takeoff using rockets, a total average thrust of 4,178 pounds of force is required, assuming a 6-second burn time. This is the minimum thrust required for the aircraft to reach 250 feet per second, or Mach 0.65, in under 6 seconds. Using open motor, a solid rocket motor was designed that produces an average thrust of 2,854 pounds of force, with a burn time of 5.5 seconds. Having 2 of these motors mounted to the aircraft, 5,708 pounds force of thrust can be achieved at takeoff. Within open motor, a thrust curve was developed as well as chamber pressure and K-in with respect to time. From this graph, it is observed that the maximum thrust achieved by one motor is 3,375 pounds of force. The maximum chamber pressure experienced within the motor is 1,712 psi, and the peak K-in value is 611. Using this open motor simulation, it is determined that 2 of these P 12,697 motors will effectively accomplish the takeoff mission. Each rocket motor has a total impulse of 70,090 Newton seconds and a 194.4 second specific impulse. These motors are P-class Bates grain motors containing ammonium perchlorate composite propellant, each having a propellant mass of 81.07 pounds. The nozzle of this motor has a 1.2-inch throat diameter, 6-inch exit diameter, and a throat length of 1 inch. The divergence half angle is 15 degrees, the convergence half angle is 30 degrees, and this nozzle has an expansion ratio of 25. These motors have 6 grains. Each grain has a length of 9 inches with a 2-inch diameter core.
The PADAR is the future of radar UAS. Turn and burn.